Hello, today we are going to be continuing our look at consumer resource models by focusing on a very famous predator-prey model, and it's pretty much the simplest predator-prey model that we can look at. So by the end of today, you should understand this simple model of predator-prey interactions and the idea of neutrally stable oscillations or cycles. Okay, so in the last lecture, we met the general framework for consumer resource dynamics. Remember, we have a resource that is being renewed at some rate, and this could be plants, it could be animals, it could be just nutrients coming into a chemostat. And we have a consumer that is consuming those resources. And this could be predators, it could be herbivores, it could be parasites. We want to model this asymmetric species interaction where one species is an exploiter or a consumer and the other is a victim or a resource. We're going to be focusing today on the idea of predator-prey interactions. Okay, so recall the general model for a resource-consumer interaction. We have a renewal function, f of r. We have a mortality term or function here for our consumer, and then we have a functional response g, which is a function of both our consumer and our resource densities. And this functional response tells us essentially about the rate of consumption by our consumer. And there's also an efficiency parameter here, epsilon, which tells us how well that resource is converted into the biomass of our consumer. So pretty much one of the simplest consumer resources models we can meet is known as the Lotka-Volterra predator-prey model. So we previously met a Lotka-Volterra competition model. Lotka-Volterra predator-prey model is somewhat related to that. Okay, so here we have our prey is going to be our resource and has a constant per capita growth rate. F of r is equal to A of r. A times by r, sorry, and A is a positive parameter. We have our predator being our consumer, C, and it has a constant mortality rate. So its mortality rate, H of C, is equal to D times by C, where D is its per capita mortality rate. Again, that's positive. And we have a linear or type 1 consumption rate. So our functional response, G of CR, CNR is equal to some constant B, again positive, times by C times by R. Okay, so that means that we can put together our consumer resource model by putting in all of these different components. We have A times by R minus BCR for our resource or prey. And for our consumer or predator, we have epsilon BCR, so epsilon is that efficiency coefficient, remember, minus D times by C. Okay, so what we're going to do is we're going to work through this model. We're going to find the equilibrium of this model and then understand its stability. Okay, so if you recall, if you want to find equilibrium of a model, we can first of all think about our null clines. So let's think about our null clines for our resource. So these are going to be when dr dt is equal to 0, and that occurs either when r is equal to 0, in which case both of these terms here will be equal to 0. So r is equal to 0 is one null cline. In other words, when there are no resources in the system. And if we have r as non-zero, then we divide through by r here and here, in which case we end up with a minus bc must equal 0. In other words, our consumer must equal A over B. Remember, A and B are just parameters in our model. Okay, let's think about what happens on this first null cline here. If r is equal to 0, we need to think about what happens when our consumer is also not changing. So dc dt is equal to 0. So that means we substitute r is equal to 0 into this equation here and set that equal to 0. So that equation there, we're going to have 0 is going to be equal to epsilon BCR minus DC. And we're going to set this r as equal to 0. So this is just going to equal minus DC. So for that to equal 0, D is a positive parameter, so C must equal 0. So we have another null line here. Okay, now we want to think about our second null line. C is equal to A over B. And remember, A and B are both positive parameters, so C is also going to be positive. That means that when we substitute this into our dc/dt equation, which is epsilon bcr minus dc, remember we're setting this equal to 0 as well because we're finding our null lines for C. Because C is non-zero, we can divide by C. We have epsilon br minus d, which we can rearrange to give r is equal to d over epsilon b. So this gives us two equilibria. We have when r is equal to 0, C must be equal to 0. And when C is equal to A over B, R is equal to D over epsilon B. So our equilibria are R star, C star is equal to 0, 0, which is our trivial equilibrium, or D over epsilon B and A over B. This is our non-trivial or coexistence equilibrium. Okay, so we have two equilibria now. Now we can think about what are the stabilities of those equilibria. So if you recall, when we looked at our resource competition model to find our stability, we needed to think about our Jacobian. So let's first of all find our Jacobian matrix J. So we're taking the partial derivatives of our equations, and I'll write them up here just so we've got them. And so we have AR minus BCR, and dc dt is equal to epsilon BCR minus dc. So the first term in our Jacobian, we're going to take our partial derivative of dr dt with respect to r. So we're going to get a minus bc. In the top right, we take our partial derivative of dr dt with respect to c. So you get minus br. On the second row, we're taking our partial derivatives of our second equation, so of dc dt. And this bottom left entry here is going to be our partial derivative of dc dt with respect to r. So we're going to have epsilon bc, sorry. And then in the bottom right corner, it's a partial derivative of our second equation with respect to c. So we'll have epsilon br minus d. So that's our general Jacobian. And we want to think about what the eigenvalues of this Jacobian are at our different equilibria. So let's think about 0, 0 first of all. So 0, 0, our Jacobian is going to equal, well, everywhere that there's C and an R in the Jacobian above, they're going to go to 0. So we're going to have A, 0, 0, and minus D. So because this is a diagonal matrix, we can write down our eigenvalues straight away. Lambda 1 is equal to A, which is positive. Lambda 2 is equal to minus D, which is negative. So 0, 0 is a saddle. Eigenvalues have opposite signs. Therefore, our equilibrium at 0, 0, the trivial equilibrium, is a saddle. Okay, let's think about D over epsilon B and A over B. So this is our coexistence equilibrium. Now, again, we substitute in our values for R and C into our Jacobian. So we have A minus B times by C, where C is A over B, sorry. So we're going to have B times by A over B. So we're going to have A minus A, so this top left one is going to go to 0. The top right, we're going to have minus BD over epsilon B. The B's will cancel. In the bottom left, we're going to have epsilon BA over b. B's cancel. And in the bottom right, we're going to have epsilon bd over epsilon b. Epsilons and b's cancel, so we just have d here and a minus d. So we have 0 in the top left, minus d over epsilon in the top right, epsilon a in the bottom left, and 0 in the bottom right. Now note, this is not in diagonal or upper triangular form or lower triangular form, so we can't write down our eigenvalues immediately from this. We could, at this point, find our trace and find our determinant, and then find out, look at the signs of those, or we could find our eigenvalues. I'll do both of those to illustrate how we find them. Okay, so if we want to solve our characteristic equation, determinant of our Jacobian minus lambda I, where lambda is going to be our eigenvalues. Our characteristic equation is that matrix, the determinant equal to 0. So if we solve this, we're going to get a lambda squared plus AD is going to equal 0. It's going to be our characteristic equation. So recall what we're doing here. If we look at our J minus lambda I, just to make sure what I'm doing here is clear, we have a minus lambda minus d over epsilon, epsilon a, and minus lambda. And we find the characteristic equation of this and set it equal to 0. This characteristic equation of this, we're going to have minus lambda times by minus lambda, so we get a lambda squared, minus, and then this minus here, they're going to cancel out, so we'll have a plus epsilon a d over epsilon, so the epsilons cancel, and we end up with a plus ad. So that's where this equation here comes from. So if lambda squared plus ad, a and d is equal to 0, and a and d are both positive. So that means that we're going to have complex eigenvalues. In fact, they're going to be imaginary eigenvalues. If lambda is going to equal plus or minus I times by the square root of AD. So we have complex eigenvalues. In fact, they are complex eigenvalues with 0 real part. So eigenvalues are complex with real part of lambda being equal to 0. And this tells me that we have a center. The other way of doing this is by looking at the trace and the determinant. So let's do that instead. We define tau to be our trace of our J, our Jacobian here. That's just going to be 0 plus 0. And now our determinant, we'll call delta, it's going to be 0 times by 0 minus d over epsilon times by epsilon a. So we have 0 times by 0 minus d over epsilon times by epsilon a, which is equal to ad, and this is positive. And together, this implies that we have a center. So you could either find this by finding the eigenvalues directly using the characteristic equation, or you could look at the trace and the determinant. And then if you recall from the diagram that we've seen previously, which shows, looks something like this. If we have our trace and our determinant here, and we have a curve that looks something like this, which is our trace squared equal to 4 times by our determinant. And our determinant is negative. We have a saddle in this bottom region here. We have a stable spiral or a stable node when we have a positive determinant and a negative trace. When we have a positive trace, then we have an unstable spiral or an unstable node. And that's when that positive trace is combined with a positive determinant. And then when we have a 0 trace and a positive determinant, which is the scenario we're in here, we're on this green shaded bit here on this axis. And there we have a center. Okay, so we found the stability of our saddle, our non-trivial equilibrium, which is a saddle, which means that we move towards it in one direction and away from it in the other. In fact, this can be understood biologically, saddle here. If we have no resources in our system, if we have no prey, the predator has no growth rate, so it has a negative growth rate, and therefore it will decay to zero as well. So if there are no resources in our system, no prey, our consumer, our predator will tend towards zero, so it will die out. Whereas if we have no consumers in the system, if we have no predators, then our prey will just grow exponentially. This can be understood as well if we go back to our original equations. If we set r is equal to 0, then dr dt is going to be equal to 0, so we will both be equal to 0. This term here will be equal to 0, and so this equation here will be negative, so we're pulled towards the origin, 0, 0, when there are no resources. And then if we think about what happens if there are no consumers, this equation goes to 0, sorry, this term goes to 0, this term and this term go to 0. So there's no change in our consumer, but we have a times by r, which is going to be positive. So we are pulled away from the origin if we just have prey and no predators. That tells us why we have a saddle at the origin of the trivial equilibrium. And the center at our non-trivial equilibrium means that we are going around in ellipses. So we have our non-trivial equilibrium, and we are going around in ellipses, and these are neutrally stable oscillations. So our density of our predator and prey, they're oscillating, they're fluctuating through time, but the amplitude of those oscillations depends on our initial conditions. So whether you're on this inner orbit or this outer orbit or anywhere in between. So this means that our oscillations are structurally unstable. They're known as neutrally stable oscillations. They're unstable or neutrally stable because deterministically you will stay on them, but with the noise that you'd experience in the real world, random effects, you would move around and you would not be pulled back to the same orbit that you started on. Okay, so that's a rough interpretation of those dynamics. Essentially, we're saying that when both species are present, they will oscillate in population density, and the size of those oscillations are determined by those initial conditions, so which of these red orbits you'd be on. So imagine here we've got our resource density and our consumer density, and we'll be oscillating something like this. We don't actually know at this point the direction of these oscillations. I've only drawn these in by thinking about the direction field, about what happens when we have no resources. We tend towards the origin, and if we have no consumers, we move away from the origin along with this axis. And due to the continuity of this system, the arrows here and here, and consequently on the rest of the orbit will match those that are on the axis. So what we're saying here then is if we imagine what happens if we initially start off with not many consumers and not many resources, so not many predators and not many prey. So if you start off with this pink dot here, your resources, your prey population is going to increase. As they increase, you reach a point where they start getting heavily predated on by a predator. So eventually the prey density, our resource is going to start decreasing as our consumer is increasing. So the predators are eating lots of prey. Gets to the point though where the resources, our prey population crashes to a low level, and now there's not enough food to go around for our predators, for our consumers, and therefore our predator population crashes and the cycle starts again. Okay, that's the end of this lecture on a simple predator-prey model. As we've seen, there's an issue here in that our oscillations are structurally unstable. And so that means that this is not a particularly good biological model. So next time out, we're going to be thinking about how we can make a different predator-prey model and seeing whether this affects the dynamics of the system. Now, this model was inspired by data on snowshoe hares and Canadian lynx. And this data is on the number of pelts that were caught, stretching all the way back into the mid-19th century. It's one of the best early data sets that we have in mathematical biology. And there were these oscillations in hare and lynx pelt numbers, and by proxy, the population sizes of these predators and prey. And what we notice here is that we see cases where, say, the number of hares increase, and then the number of lynx increase, and then the hares decrease, followed by the lynx decreasing. And we see this kind of pattern quite nicely over here, for example, hares increasing here and here and here, before lynx increase, and then subsequently hares fall and the lynx population crashes. So this kind of cyclical dynamic between predator and prey is quite nicely rooted in data. But as I've just mentioned, this particular model that was inspired by these lynx hare cycles is not a particularly good biological model because these oscillations are structurally unstable. What that means is that eventually they would hit the boundaries, our C or our R axes, and then one of the populations would be driven extinct. So in the long term, they can't persist in these mathematical models. So what we're going to think about next time is are there ways in which we can still get these types of dynamics by looking at a more advanced predator-prey model. Okay, today's self-study problem is to have a go at sketching the phase plane. So work out what the direction field is on your null lines, sketch those null lines along with the direction field, and then plot example trajectories. Okay, thanks very much. I'll see you next time.